for joining us today. We're about to get ready, so please stick around.
Oh, wait.
Heinmiller?
Yep.
Drew Heinmiller. Hi, and thanks for joining us today. I'm Betsy Young with The Scientist magazine, and here we have Drew Heinmiller, who is with FUJIFILM VisualSonics. I'd like to tell you a little bit about what we're doing here today, and then I'm going to turn it over to Drew. We'll have a little conversation about his new product, the science they're talking about here at Neuroscience, and anything else that's on your mind. Great. So could you tell us a little bit about you and your company?
Sure, yeah. So I'm the product manager at FUJIFILM VisualSonics. We make high-frequency ultrasound equipment. So people ask, what is high-frequency ultrasound? Is it the kind of thing you see in the clinic? It's very similar, but in the clinic you're using, say, the 1 to 10 megahertz frequency range of sound. We're in the 15 to 50 megahertz range. So we're much higher frequency, which actually ends up being much higher resolution. So with high resolution, we can go down to about 30 microns. So this is a huge advantage. The trade-off is depth. So we're going down about 3.5 centimeters, which is great for imaging animals. So small animal imaging and that kind of thing. I would say our main sort of application is cardiovascular research. Right now, the American Heart Association is having their big conference out in Anaheim, and we've got a bigger booth than this there right now. And that's where all the cardiovascular researchers are really looking into it. Ultrasound is used very commonly in the clinic for cardiovascular research. So for preclinically, for heart models, infarct models, this kind of thing, just measuring cardiovascular health in general, it's a very common tool in drug development in a lot of different application areas. Cancer is another big application for us as well. But we've got our head office is up in Toronto. We have an office in Amsterdam as well, and then we have systems all over the world. There's literally thousands of systems out there right now.
Great. Now, I know you're here to talk about ultrasound and photoacoustic imaging. Can you tell me a little bit about those technologies and how they're being received by the SFN audience?
Sure, yeah. So I'll start just by describing a little bit what photoacoustics is, because perhaps a lot of your listeners aren't really familiar with it. So ultrasound is great. You send sound in, it reflects off surfaces with different abilities to reflect or transmit the sound, and you generate an image from that. A typical sort of black and white image that you see of people, of their developing fetus or something like that. With photoacoustics, we're actually using pulsed laser light to generate ultrasound. So we send this pulsed laser light into the tissue. Anything that absorbs that light heats up a little bit and gives this thermoelastic expansion effect, which results in a pressure wave through the tissue, which we then detect with our ultrasound detector. So instead of sound in and a reflection event and sound out, we put light in, we have an absorption event, and we get sound out. And what absorbs the light that we're using in the body of an animal? It's mostly hemoglobin. And this is a really kind of nice thing that we can actually image with several different wavelengths in the near-infrared range. Hemoglobin absorbs, and whether it's oxygenated or deoxygenated, you'll actually get a different signal. So it's basically the difference between red and blue blood. So now we can actually measure how much oxygen the blood is carrying completely non-invasively, like you would do, ultrasound being a non-invasive modality. Now, okay, great, that's photoacoustics, but why is that useful? Why are we here at SFN? Well, one implication is if you can actually measure with high resolution, remember, because we're using the ultrasound to focus, if you can actually measure oxygen saturation with high resolution, if you can do that in the brain of an animal, there's a potential for doing functional imaging. So that's why we're here at SFN. We've been here for a couple of years. There are implications for different application areas, one of which is stroke. Now, I know that's strictly speaking not really neuroscience, but really being able to measure sort of infarct in the brain is one obvious area. But another one is just that sort of brain vasculature and how to measure that function using photoacoustics. Another application is, because we are in small animals and we do have this nice resolution, we can use both the oxygen saturation information that we get, but we can also get flow from Doppler ultrasound or perfusion with microbubble ultrasound. So we're really trying to present here our product, specifically the Vevo LAZR-X. It's our new photoacoustic and ultrasound imaging product. We're really trying to emphasize that you can use multiple modalities to learn more about any one thing than you could with one modality alone.
That's so great. Now, what is the level of, how deep does the laser go? How deep can the laser see? Do you need transparent mice, or can you use normal living mice?
Yeah, that's a great question. So we are somewhat limited because it really is a hybrid optical ultrasound modality. We are limited in some ways in what the optics can do. So you have to get light in there. That you point out very, very well. Like, you have to get light in there. So we can see down, and with the ultrasound we're looking about the 3.5 centimeter kind of range. That's our maximum depth. With the photoacoustics, we're looking at the 1 to 2 centimeter range. So we are limited. You have to get enough energy in the tissue to be able to get a signal back. Now, do you have to have transparent mice? That's another great question. So when the light strikes the surface, it scatters and goes everywhere, unless your mouse is transparent, where it'll go straight. We actually don't need the light to go straight, because we're not detecting the optical signal coming back. We're detecting the ultrasound, and the ultrasound goes straight. Essentially, the animal's transparent to ultrasound, so we can get the ultrasound straight back out, and that's how we get that really nice resolution, because we're not relying on being able to see through a transparent mouse optically. So that's the kind of nice pairing that we get with the optics, where we can see an optical signal, and with the ultrasound, where we can actually resolve it at depth, and that depth typically being around 1 to 2 centimeters.
Great. Can you tell me anything about other applications for this technology? What else have you tested it in?
Yeah, great question. So, as I was saying before, a lot of our customers are cardiovascular researchers, so there is a lot of interest to use photoacoustics to measure, cardiovascular infarct. So an infarct in the myocardium, for example, just sizing the infarct, that kind of thing. Cancer is another huge application area. So, for example, soft tissue, tumors that are growing, you want to be able to assess the microenvironment, and that has to do with things like blood flow, the perfusion, the hypoxia in the tumor. That's a huge one, where you get these hypoxic areas of tumors that have higher metastatic potential, different genetics even. So that's another area where it's really on the sort of functional side. And of course, with any anatomical imaging that you get with ultrasound, you can do sizing. So tumor sizing, just measuring whether your treatment is working based on how the tumor is shrinking, for example. So cancer is another big area. I'd say another area is probably developmental biology, where you're looking at placental oxygenation. So again, this is a really important thing to be able to assess maternal health and the health of the fetus, how well oxygenated that placenta is. Now, you can go one step further as well, because you can use any optical absorber in the range of light that we're using. So you can use, for example, nanoparticles or dyes that absorb in the near infrared range, and they'll give you a signal back. So now you get into molecular imaging, where you can actually have specific molecular signals. You have, let's say, your antibody tagged with a dye, for example, and then you're able to track where those antibodies end up. Doing things like biodistribution studies, targeted molecular imaging studies, even things like blood-brain barrier disruption, where you can deliver a dye, disrupt the blood-brain barrier either with drugs or maybe a high-intensity focused ultrasound, and then see the leakage of those particles into the brain parenchyma, and then do that completely non-invasively. And then, of course, it's a longitudinal imaging modality where you can image the same animal over and over and over again, so you can follow things like treatment and that kind of thing.
Do you see this as another application for optogenetic studies?
I've been asked that. That's a good question. I've been asked that before. My understanding is with optogenetics, they're really focusing the light on very, very specific areas. But there's potential there. I mean, we're using this pulse laser light. If you had, some kind of, optogenetic probe that was sensitive to those wavelengths, you could potentially do the imaging and the stimulation at the same time. I'm going to have to walk around and talk to some of the other companies that do that. It's not my area of expertise, but yeah, that's a great question.
Great. Now, is there anything else you can tell us that you've been hearing from the scientists you're talking to today? What is hot, and what are people interested in neuroscience research?
Yeah, good question. I mean, just, the people that are coming to the booth, I haven't had a chance to walk around yet, but the people that are coming to the booth, a few of them have actually asked about focused ultrasound for stimulation of neurons. So you can actually use focused ultrasound to stimulate neurons and to activate neurons. One researcher was asking about doing that in the retina. Can we do that? I would say, our system is designed for imaging, not so much therapy. But that's sort of a thing that's piqued my interest a little bit. I've had a few inquiries about that, and yeah, maybe there's some nice synergies there where we could pair up with companies that make the transducers for doing the stimulation, and we could do the sort of functional imaging part of things.
Great. Just one more question for you. Is our current understanding of photoacoustic imaging sort of at its limit, or do you think there will continue to be developments in that area?
Photoacoustics is new. I mean, it's a really new imaging modality. The photoacoustic effect was discovered actually by Alexander Graham Bell over 100 years ago, but because laser development didn't catch up until fairly recently, it's actually so new. So we were the first ones to release a commercial photoacoustic imaging system, and that was back in 2011. So this is a really new modality. There's a lot more research and development that's going on and will go on, and I actually see it as getting a bit more of a foothold in the broad sort of biomedical and medical research community over the coming years. So I'm really hoping that that we can really get new data that we haven't been able to get before from this new modality.
That's excellent. Thank you so much for joining us today, Drew.
Hey, thanks a lot.
I'd like to thank our audience for tuning in. We'll have other videos throughout the rest of SFN, so stay tuned.